graphing rational functions. A rational function is really a ratio between two polynomials. Here's an example where the polynomial on the top is a higher degree than the bottom, and we notice we get these slant asymptotes. As x gets large, it goes kind of at a diagonal. Here's an example where they match. Second degree over a second degree polynomial, the ratio, we look at the leading coefficients, and it goes to 1. In the other case, what if the top degree is smaller? Here's the first degree divided by a second degree. Well, then it eventually goes to 0 if x is large enough on the right or small enough on the left. And then we have vertical asymptotes too. That's caused by division by 0. Here, when x is 0, we have a vertical asymptote. Here, when it's plus or minus 2, we have a division by 0, and it goes to negative infinities inside and positive infinities on the outside. And here's another one, plus or minus 1. And again, two possibilities. It either goes to a negative infinity or a positive infinity. To analyze them, we're going to look at the 3 zeros and the 3 possibilities for the extreme behavior. When I mean by 3 zeros, that means the top polynomial has zeros. Whatever makes the numerator 0 would be an x-intercept, because a fraction 0 over something is really going to make the whole fraction 0. The zeros at the bottom, though, cause a division by 0. So the two possibilities on either side are either to positive or negative infinities. Finally, it's easy to compute f of 0. Let x be 0, see what you get. That gives you your y-intercept. At the end behavior, a positive or negative infinity, depends what goes on with the degree. The top degree is smaller than the bottom degree, it'll go to 0. If the top degree matches the bottom degree, it goes to the leading coefficient ratio. And if the top degree is larger than the bottom degree, we divide and ignore the remainder. First off, let's take a look where the top degree is smaller than the bottom degree, and so it eventually goes to 0. Here's a first degree over a second degree, so we know it'll eventually go to 0. We'll put a horizontal asymptote here, y equals 0. Then let's take a look at the 3 zeros. What would make the top part 0? Well, 2. Well, that means there's an x-intercept at 2. What would cause the bottom division by 0 would be negative 1 and 3. And so these will be vertical asymptotes at negative 1 and at 3. This multiplicity is odd, so if we were to figure out what f of 0 is, we notice that's 2/3. So it's going to come from above, and it's going to cross over, looking like that. Now, the behavior at the ends, either it will be positive going up to positive infinity, or it'll be negative. And the same thing at this end. So what we're going to do is we're going to look at some samples. For instance, is negative 2, and we put in our function, will that be a negative going below or positive going up? Well, we place x as negative 2, and we get a negative number, so it must go down and always be negative. On the same end, if f of positive 4 to the right of this asymptote, is that positive or negative? Well, we evaluate f of 4. It's positive, so that means they're all going to be positive because they do not cross the x-axis. Second is when the degrees match. Here's a second degree divided by a second degree. So the trend is to look at the leading coefficients. In this case, that's 1x squared divided by 1x squared. So f of x is going to go to 1, and that'll be the horizontal asymptote. Now looking at the 3 zeros, at the top we see plus or minus 1 would zero that out, and that will be our x-intercepts. And we look at the bottom, x equal plus or minus 3, we have a division by 0, and that's where the vertical asymptotes go. So now we evaluate f of 0. We get a positive 1/9. So if it's positive here, it must be positive in between negative 1 and positive 1. So the middle will look like that. And of course, since we don't have any x-intercepts here, everything must be positive on either extreme. Our final example, when we have a third degree over a second degree, we have the situation where the top degree is larger than the bottom degree. And the idea here is to divide and ignore the remainder. So let's do a little bit of division. We look at the leading terms. X times x squared will give us x to the third. Multiplying that to both, we have x to the third minus 16x. And then we look at the difference here. Negative 2 times this is going to give us what we need. And we don't need the remainder. We could just look at y equals x minus 2, and that will be the behavior in the extremes to the right and left. It'll eventually look like this line. Now we still look at our three zeros. I factored the top to realize that the zeros at the top are going to be at negative 2, 3, and 1, which means those are the x-intercepts. We look at the zeros down below where division of 0 happens. We see that at positive and negative 4, and so those are the vertical asymptotes. Looking at the behavior at the extremes, look very clear to be positive on the right and negative on the left. And here we should probably look at f of 0 to see what goes on in the middle. Well, when we put x equals 0 to evaluate f of 0, we get a negative 3/8. So it's down below, which means it goes up to the 1 and up to the negative 2. Something like that. And of course, the extreme behavior, it doesn't cross the x-axis. It will be positive on the right and negative on the left.